Okay, Assalamualaikum and good day. So for now, we look at Fourier series, where it is an expansion of a periodic function fx in terms of an infinite series in sine and cosine. That means the function itself repeat its pattern at some period. Okay, there are a lot of applications of Fourier series in real life. For example, in acoustics, electronics, communications, signal waveform, and also in heat conduction. Okay, as you can see for heat electronics or signal waveform, that means we have many waveforms. Okay, so that means some wave repeats at one periodic times. That's when we use Fourier series. Okay, the definition of Fourier series. Let f be a function defined on the interval negative L to L. So the Fourier series of f is given by this formula. Okay, fx equal to a0 over 2 plus summation from n to infinity an cos n pi x over L plus b of n sin n pi x over L, where we have here a0 is equal to 1 over L integrate negative L to L fx with respect to x. An is 1 over L integrate negative L to L fx cos n pi x over L with respect to x. And Bn is equal to 1 over L integrate negative L to L fx times sin n pi x over L with respect to x. Okay, so next, let's say if we have fx is defined on the interval c to c plus 2L. That means here it is not from negative 1 to 1. If negative L to L is actually, for example, x between negative 1 to 1. So let's say for this one, it is not from x between negative 1 to 1, where is this one differ actually. Okay, for this one is actually from c x to c plus 2L. Okay, for example, we have the interval is from 0, x between 0 to 3. Okay, that means here we will integrate from 0 to 3. That's what it means. Okay, so 1 over L still we need to calculate for the period. Okay, so it just change here. Instead of negative L to L, it will be from C to C plus 2L. Okay, this is for the intervals where the lower boundary and the upper boundary is not the negative value of each other. Okay, so next, for the expansion of a periodic functions in Fourier series. For example, we have here, we need to expand this piecewise function in a Fourier series. Okay, the first, what we need to calculate is the value of L. Okay, as I mentioned earlier, first, 2L is equal to upper boundary minus lower boundary. So that means pi minus negative pi, which is 2L equal to 2 pi. That's why we will have L is equal to pi here. Okay, so next we need to calculate for A0. A0 is equal to 1 over L, so 1 over pi. Okay, integrate from negative L to L, means integrate from negative pi to pi. Okay, fx with respect to x. Since we have a piecewise function, we need to separate them. Okay, that means first is 1 over pi, it's just a constant. So we open a big bracket, okay, a square bracket here. Integrate from negative pi to 0 would be the function is 0 here. That's why it is 0. And then from 0 to pi, it is pi minus x. Okay, integrate as usual. For 0, it should be equal to 0. Then this one is 0. So we just have to consider this pi. So integrate this one is pi x minus x squared over 2. Substitute value from 0 to pi. Okay, remember upper boundary minus lower boundary. Okay, although it is a common thing that you should know by now, but I still need to remind you, it should be upper boundary minus lower boundary. Okay, that's how you substitute the value. Okay, so right now we have A0 equal to pi over 2. Next, calculate for A of n, which is 1 over pi, 1 over L, 1 over pi. Integrate from negative pi to pi. fx cos nx dx. Why nx? Because here cos n pi x over L. Okay, you can just simply write it like this at first. 1 over pi, integrate negative pi to pi. So here is fx cos n pi x over L, which is pi dx. What we did next is cancel off pi, and hence we have equal to 1 over pi, integrate negative pi to pi, fx cos nx dx, like this. Okay, that means from here it's better for you to do this first. Okay, because this is a simplification of these terms. Okay, so next, since from negative pi to 0 is 0, so it is 0. Anything multiplied with 0 should be 0. So here from 0 to pi, fx is pi minus x times cos and x with respect to x. So we need to integrate those. As you can see here, we need to use the integration by parts. Okay, it's easier for us to use this tabular method. So u is equal to pi minus x and dv is the part of cos and x. Remember how to choose u and dv. Okay, we have logarithmic function, index, algebraic functions, trigonometry, and exponential function. That means we come across a first. That's why we let u as the algebraic functions. We let the algebraic functions as u. Okay, so u is equal to pi minus x, and dv here is cos and x. So this part you need to integrate. This part you need to differentiate. Okay, so here differentiate pi minus x is equal to negative 1. Differentiate negative 1 is equal to 0. Okay, and for this side it should be cos n x. Integrate cos n x is 1 over n sin n x. Okay, I would prefer you to write it in this term. Okay, this one it is much safer if you write it in this term, because I'm afraid that there might be someone cancel out n here, which is totally wrong. You can't simplify the angle for any trigonometric function. Okay, so next, integrate 1 over n sin n x. So nx, that means we have here 1 over n squared. Integrate sin is negative cos nx. Okay, it's better for you to write in this form, okay, rather than this. Okay, next, how do we do it? So it should be here a diagonal arrow. So it is here, and another one until it is 0. So let's say this one that is the value, so you need to continue until before 0. Okay, so it will be alternate, plus minus plus minus. Okay, plus minus plus minus plus minus, it goes on. Okay, so right now integrate 0 to pi minus x cos n x with respect to x is equal to pi minus x here, pi minus x times sin nx times the positive. So it should be pi minus x over n sin nx. Negative times negative times negative should be negative. Negative 1 times here should be cos nx over n squared, or you can write it as this way. Okay, and then substitute the value from 0 to pi. Okay, here after we substitute the value, we come to this term, whereas an is equal to 1 over n squared pi, 1 minus cos n pi. Okay, cos n pi can also be written as negative 1 power of n. And sin n pi is always going to be equal to 0. Okay, the reason behind it, let me do a quick review. Okay, this is the graph for sin x. That means here. Okay, we are done. Here should be negative pi. Here is 0, pi, 2 pi, and here is 3 pi. Okay, as you can see, sin n pi equal to 0, because for every n pi, that means negative 1 pi, 0 pi, n equal to -1, n equal to 0, n equal to 1, n equal to 2, n equal to 3, the value here, y is equal to 0. Okay, that's why sin n pi equal to 0. But as for cos, it should be this way around. Okay, wait a second. I think I might do something wrong there. Okay, wait a second. Sorry, I'm just gonna draw it on another axis. Okay, here is 1 and here is -1. Okay, here is for pi. Here is 2 pi. Okay, and here is for -pi. Okay, as you can see here, when n equal to 0, it is equal to 1. That's right, because cos n pi is equal to -1 power of n. Anything power of 0 is equal to 1. Okay, next. When n is equal to 1, here, the value of y is actually -1. So, -1 power of 1 is equal to -1. And then for 2, that means here is -1 power of 2, which is 1. This one is -1 power of 1. And for this one, n equal to -1. So that means here -1 power of -1. If you calculate it, it should be like this actually. 1 over -1 power of 1, which also hold for -1. That's why this statement holds. That means cos n pi is equal to -1 power of n. Okay, just substitute that. And then next, we want to calculate for b of n. That means 1 over L, integrate -L to L, fx sin and pi x over L with respect to x. Okay, since this one is actually sin and pi x over L is actually sin and pi x over pi. And we can simplify the pi here. That's why we have bn is equal to 1 over pi, integrate -pi to pi, fx sin and x with respect to x. Okay, as what I did for an, you can also write it like this. 1 over pi, integrate -pi to pi, fx sin and pi x over pi with respect to x. Okay, cancel out pi and pi. Then only you come to this equation. Okay, you write that equation. Okay, next. Okay, integrate for this one should be 0 because from -pi to 0, fx is equal to 0. So from 0 to pi, fx is equal to pi minus x. So next, we still need to use integration by parts. Okay, we let u equal to pi minus x. Remember, this side would be differentiate and this side is integrate. Okay, differentiate pi minus x is equal to -1. Differentiate -1 is equal to 0. Okay, dv is equal to sin n x. Integrate this one can be also be written as -1 over n cos n x. This would be much safer. And next, integrate here is -1 over n squared. Integrate cos is sin n x. Okay, let me do a bit of correction here because of my not neat bad handwriting. Okay, now you just need to substitute here. So that means integrate 0 to pi minus x sin n x dx. Open the bracket here. It should be negative pi minus x over n. Here pi minus x plus times negative is negative. So that's why negative pi minus x over n cos n x minus sin n x over n squared. Okay. Or you can simply write it like this actually. B of n is equal to 1 over pi. Open the bracket. Okay, we have here negative pi minus x over n. It should be minus. Okay, pi minus x over n cos n x. And then minus is plus. Plus 1 over n squared sin n x 0 to pi. And it can then be written to this directly. Okay, substitute the value and hence we have bn is equal to 1 over n. Hence, the Fourier series here is defined as fx equal to, here is a0 divided by 2. The value of a0 that we have obtained earlier is actually pi over 2. That's why here we have a0 over 2 pi over 4 plus summation n from 1 to infinity. Here is an cos n pi x over L, which is nx, okay, plus bn sin n pi x over L, which is nx. Okay, this should be in the summation n from 1 to infinity. Okay, this is your fx. Okay, a0 is actually pi over 2. Okay. I'm just gonna write something for an here. Okay, this one, the same for bn. As bn, you can also directly write it as such. Okay, that means here pi minus x over n sin nx minus 1 over n squared cos nx 0 to pi. Okay, you can write it directly there. Okay, that's all for the first example for Fourier series. Okay, hopefully you can grasp a view on how to actually solve a Fourier series. Okay, thank you class. Assalamualaikum.